let's think about another example here. Let's design a context-free grammar that generates binary strings with an equal number of zeros and ones, which we proved in the past that this is not regular. We're going to talk about how we could design a context-free grammar for this. So, start simple. Now, you might say, Dan, what are we going to do with this one here? So think about it. What's the form going to look like then? What's the form going to look like? Now, I must stress that it's just an equal number of zeros and ones. It's not that it isn't just a whole bunch of zeros then a whole bunch of ones, which we proved that that isn't regular, right? We proved that. However, this right here doesn't require it to be that the zeros and ones are exactly like they're all the zeros then all the ones, right? So we have to be a bit careful about this. This one's a little different. So first we know that you can have 0 zeros and 0 ones, right? So we know right away we need that. We need the empty string. So how can I create strings that have equal numbers of zeros and ones? Well, you can think of it where there's a 0 and a 1. It could be where there's a 1 and a 0, right? These are both strings that would satisfy this right here, right? Well, let's take tips from our previous example with the palindromes. Maybe we can introduce a variable in between like this so that we can guarantee that we can create patterns that look like equal numbers of zeros and ones. So why don't we introduce these? Now, you might be saying, Dan, is that enough? Like, is that all we need? Well, I got some bad news. That isn't enough, actually, is that we include SS. So notice that this will allow me to get two groupings, because notice there's zeros and ones. There's two possible symbols. I mostly wanted to throw this one out there because it's a little bit more tricky. I thought it'd be a good idea. Let's do a couple more. So I thought we would consider another one, but I'm going to do it the other way around. I'm going to give you the context-free grammar, and we're going to try to figure out what language it is describing. So start symbol, it's going to be 1, and then, sorry, A and then 1. Then it's going to have another variable. It's going to be for A, it's going to be 0, A1, or epsilon. What language is this describing? Well, you know right away that there's going to be a 1 at the end of the string. That you could tell right away. Why? Because S gets replaced by A, then a 1. But there's nothing that comes after the 1. So you know there's a 1 already at the end. So let's look at A. And it says 0, A, 1, or epsilon. So if we stopped at A and put it here, it'd just be a 1, right? If I introduce this to replace A, then I would have 0, A, 1. Introducing a 0 and A, then there would be a 1 right beside the 1, right? And if I did this again, I would have 0, A, 1, but it would be 0, 0, A, 1, 1, 1. And I can always stop this process whenever I want to replace A with the empty string. So what does it look like then? So we know it does generate this string. It generates that string. It generates, actually, does it generate this one? No, it generates this one. Why? Because you start off with this, and then you would have 0, 1, 1, because that's already over there. So these are all strings that get generated by this grammar. So what's the language then? It's always going to be, it'll look like this. The language of this grammar is going to be 0 to the n, 1 to the n plus 1, such that n is greater or equal to 0. And we already established with some of our discussions how you could prove this language isn't regular. So let's consider another example. This one's a little trickier. But let's take advantage of the fact that when I introduce symbols into the as part of the production rules, these terminals, I actually have control over making sure they have equal counts. So if I do it carefully enough, I should be able to keep this in mind if it has a particular form. So when I don't have a particular form, where it could be wherever, you have to take into account that it could land way over here, it could be way over there. I don't know where it could be, but it has to be present. So let's design a context-free grammar for the language L. It's going to be A to the N, B to the M, C to the K, such that K is going to be equal to N plus M. So what does that mean in plain language? It means that the number of C's is equal to the number of A's plus the number of B's. So when you see something like this, you know whenever a C appears, what happens? Either it's going to be an A or a B that has to match it. The minute you observe this, the faster this becomes an easier thing to play around with. So I'm going to introduce a start symbol. I'm going to fill something right here in a moment. So let's think about what that means then. So it means that if I put an A in, it means that I have to have a C, right? But remember, I can't get to starting putting B's in until I'm done and committed with the A's. So it means that I'll have to repeat this process. Every time I put an A in, I got to introduce a C at the end. A at the start of where I am at, within the context I'm playing within. I'm going to have to put a C at the end of whatever context I'm within. Once I'm done that, I'm going to move over to the B's and putting the B's in. So whenever I put a B in, I got to put a C in. But when I'm done this process, I'm done, right? I don't need to do anything else. Why? Because I already have introduced the C's. Do you see that? So it means naturally, you can think of this in a bunch of phases. So you can think of it in terms of steps, this one. So you first, you put in the A's, you put in the B's, so then you end because the C's are included, right? So I start this up. This will introduce A's. Every time I put in an A, it puts a C at towards the end of the string. And then when I'm done with this, I can replace the A with a B, and then I can start putting in B's after the A's, but before the C's. And then when I'm done that, there'll be a bunch of C's at the end. But notice every time I put an A in, it puts a C in. Pretty nifty, right? So those are some examples of context-free grammars.